Bismillahirrahmanirrahim. In this lecture 8A of our course on real statistics and Islamic approach, we will discuss the concept of probability. As we have seen, this is needed to distinguish between situations where something happens at random due to chance and whether the alternative is that there is some real significant force which is creating the pattern that we see. It is not just a random pattern. A serious problem with discussing probability is that none of the existing definitions of probability make any sense. As Russell said, that probability is the most important concept because nobody has any idea what it means. A review article in Stanford Encyclopedia of Probability by Alan Hayek mentions at least 6 different contradictory definitions which are not compatible with each other and each of which have significant flaws. The dominant definition, the one which is given in 90% of textbooks, is probability as limiting frequency. As we'll see, this makes no sense at all. And there are many other major schools of thought, but none of them really make any sense. So why is it that no one has been able to come up with a clear definition of what probability means? We will briefly discuss that there are 2 major reasons for this. One is a Newtonian picture of the world as a mechanism, as a deterministic system. And the second is the philosophy of empiricism and positivism, which started with Hume, which tells us to focus on observables and to ignore unobservables. A deterministic picture of the universe tells us that what happens tomorrow is a function, a deterministic function of what the initial forces. So nothing really is random. So if we think that there is a randomness, like when a coin is flipped, it is only due to our ignorance. So basically probability is a state of the mind. It is not a part of external reality. This makes it very difficult to come up with an understanding of genuine probability, which is part of external reality. A second problem was the philosophy of empiricism or logical positivism, which has dominated thinking in the West for a long time. And basically this says that we should look only at what we can observe and we should not speculate about what cannot be seen. And this basically arose after the rejection of religion in the West. And the idea was that religion is concerned with the unseen and science is concerned with what we can see. Unfortunately, when it comes to probability, there is only probability is concerned with what might have happened, and this is by definition unseen. So all attempts to reduce probability to the seen, which is basically what definitions try to do, fail because you have to deal with what might have happened. So these 2 basic philosophical problems, a deterministic mindset and a positivistic mindset, make it impossible to understand what probability is, which is the reason why nearly all major definitions that you can find of probability are wrong. The random variation that we see is part of external reality. It is not part of our mindsets, but how to understand this, how to formulate this, this has been the subject of a huge controversy. So in this lecture, we will provide a new definition of probability, which is suitable for the purpose that we are looking to understand probability, which is to distinguish between chance variations and genuine differences. And so we will call this conjectural probability. It is based on guessing, making certain guesses about what the probabilities might be. There is one essential feature of probability which is not incorporated in the existing definitions to the best of my knowledge. A random event like a coin flip or any other thing is random before it happens, but after it happens the probability is extinguished. It no longer exists. One of the 2 or several possible outcomes occurs. So probability exists before the event and does not exist after the event. So this temporality, this sequencing, this time is an essential feature of probability. But none of the models have this feature, so we will introduce a model which incorporates this in a very serious and significant way. Here's a picture which explains our definition of probability. We start with a random event like a coin flip. So you have a coin in your hand and you're trying to flip it. So before the flip, there is a probability. There is a probability that the coin will come up heads and the probability that outcome will be tails. No one actually knows the probability, but our experience and symmetry of the situation suggests that the two probabilities should be 50%. So after the outcome, once the coin is flipped and we see what happens, there is no more probability. One of the two outcomes has occurred, and after this time, basically the world is split into two worlds. There is one world in which the coin was flipped and the outcome was heads, and there is another world in which the outcome was tails. These two worlds are separate, disjoint from each other. Things which happen in one world do not refer to what happened in the other world. The other world is an imaginary world. And so now there is subjective probability also in this model. Subjective probability arises if we don't know what happened, but we are operating in a period in which the probability already, the event already occurred. So after the event, since there is no longer any probability, we can talk about confidence. Suppose that the coin was flipped, but I don't know what happened. Then I can have confidence. Confidence is a word which is sort of equivalent to probability, but it reflects our state of knowledge about what happened rather than something in external reality. So this basically nearly all the literature fails to put in time and fails to put in the distinction between the probability and confidence, what happens before the time zero and what happens after zero. And this is one of the reasons why the existing definitions of probability are confused. So one of the issues that arises in this model of probability is that how do we know if when we flip a coin that the probability is 50% of heads and 50% of tails? This is called the problem of single case probability and is a difficult problem. So to answer this, we have to look at our understanding of what science means. There is this book called What is This Thing Called Science? And this whole book is a philosophical approach, and it shows about many different ideas about what science is. And there is, again, no satisfactory answer. But basically, the theory that I propose is called critical realism, and it says that science is about making guesses about the unobserved reality. These guesses can never be confirmed directly, and you can only have indirect confirmation. So there is no way to arrive at the truth, no way to know for sure that our theory about what is happening is true, but we get indirect confirmations. So just like on the basis of this theory, just like this scientific theory, our idea about probability is a theory about something which we can never actually observe. So we have a theory that based on how we see the coin flip, that it is a fair flip and that the probabilities are 50%, and then we can check what happens and see if our theory matches what we see, in which case we get indirect confirmation for the theory. We will see how this works by examples. So I'm going to give several examples of conjectural probability. So this is the example that we have been discussing, that if a coin is symmetrical and conditions of flipping are sensible, then we might think that the probability of the two outcomes, heads or tails, is equal, and therefore it's 50%. Once the coin is flipped, then this probability no longer exists. But if someone doesn't know what the flip is, he can call the flip, and he can have certainty, he can have confidence 50% that it is heads or tails. So these two things have to be distinguished: what happens before the flip and after the flip. After the flip, the probability is only in the minds and only due to ignorance about what happened. Before the flip, the probability is in the coin and in external reality, not part of our mental makeup. There are many other ways that probability can enter the world as our conjecture about how the real world works. So for example, we suppose that two players of a random game have equal skill at the game. This means that both have equal chances of winning. So the probability that A wins the game or B wins the game should be both equal and 50% if draw is not possible. If draw is possible, then the two probabilities should be equal, but maybe less than 50%. So if we observe a sequence of games, we can assess whether or not this assumption, this conjecture of equal skill matches what we see. If one of the player wins very often, then we will think that probably they don't have equal skill, because we can reject this hypothesis about the probability of equal skill. A very important application occurs when you have a drug and you want to assess whether this drug actually has any effect. So we take two groups of patients and we match a person in the treatment group with one in the control group on all relevant factors, and then we give the drug to the treatment person and the placebo to the control person. And now the outcome, whether both people are cured or one is cured and the other one is not, the outcome should be the same. That is, the probabilities of the outcome in treatment group and control group should be the same. So on this basis, there is a 50% chance of placebo performing better and a 50% chance of drug performing better. And on this basis, you can make probability calculations and assess whether or not this hypothesis about reality is consistent with the observations that we get from the experiment. Probability is often used to create justice, fairness. We choose players according to coin flips. And the biggest experiment like this was the Vietnam War draft lottery, where people were chosen to be sent to die according to a lottery. And the goal of the lottery was to give everybody an equal chance, all of the young people in a certain age category. So all of the birth dates were placed in a bucket and a ticket was drawn at random, and also people's letter of names was chosen at random, and that was the system used to select people to go to the war on a compulsory basis. The goal was to have a random sample which would give all people equal chances, but later examination of the data showed that this didn't seem to be completely random. Some of the numbers had higher chances of being picked than other numbers. So the null hypothesis of equal chances turned out not to be consistent with the data. There is another famous example where people in a boat decide that the coming storm is due to a guilty party among them who is fleeing, and so they choose straws to decide who is the guilty party. So in this example, one of the straws is broken off, but every person is given a chance to choose one of the straws, and but the broken part is hidden so that anybody can choose all of the straws with equal probability. So in this case, you can use the laws of probability to show that all people have an equal chance of choosing the short straw. So this is something which is apparently not obvious. At MIT, there used to be a lottery for residencies where people would be given numbers which would determine their priority in choosing housing. So students would line up early to try to get the first pick, but the numbers were being distributed at random, so actually the chances were equal. Whether you went there early or late, your chances of getting a high number were the same. But the students thought that if you entered early, you would get a better chance at picking the lower numbers. Similarly, in the straw example, since people choose sequentially, one might think that the early people have different chances from the late people. But when you do the probability calculations, it turns out that all have equal chance. Another example of how probability can come into being as a conjecture about reality is when you're testing for extrasensory perception, ESP. You take two people in two different rooms and you ask them to choose cards at random. So if the choices if the two choices are independent, the probability of match should be 1 over 52, or 1 over the number of cards. So this is a null hypothesis about the probability, the null hypothesis of independence, the conjecture of independence. It leads to probability calculations of what might happen. If the number of matches that we see is significantly higher than the prediction of independence, then we would say that we have evidence for ESP. One of the people can guess what the other person is choosing. So again, probability enters as a conjecture about the mechanism which generates real-world data. So in this final section of this lecture, I will explain how this formulation of probability allows us to explain a problem that has been confusing people for centuries, and this is called the Bayes rule. So consider a setup in which we have a box with 3 balls, 2 whites and 1 black, and we make 2 draws in sequence from the ball, from this box. So if the first draw is a black, then only 2 white balls are left, and second ball must necessarily be white. If the first draw is white, then the 2 remaining balls are white and black, and both of them have 50% chance of being picked, and that's what's pictured in this diagram. It's easy to calculate the probabilities of the outcomes. Basically, to calculate the probability, you just need to multiply the probabilities along a branch. So suppose I want to look at the probability that the first draw is white and the second draw is also white. So this is broken into the first branch, which is probability that the first draw is white, that's 2/3, and then the second probability is a conditional probability. Given that the first draw was white, what is the probability that the second draw will also be white? That's 1/2. We multiply these two and we get 2/3 times 1/2, and that's 1/3. So this is the normal calculation. Now when you don't have any time in this picture, then you can ask that the joint probability d1 equals white, d2 equals white, will also equal the other way of writing this, which is probability that the second draw is white times the probability that the first draw is white, given that the second draw is white. So this is the reverse and unnatural probability. Given that the second draw is white, what is the probability of the first draw? Now there's something strange about this, because the first draw already took place. The second draw cannot take place until the first draw has taken place. So the whole, because there is no timing in conventional definitions of probability, so this problem has been a source of major controversy and debate, with some people arguing that this reverse probability is good and valid and just like other probabilities, and other people arguing that no, this reverse probability is not valid. Here we can see clearly that when you look at it chronologically, this doesn't make sense as a probability, because the probability has been extinguished by the time you get to D2. The only issue is that how did you get into this situation where you know that the outcome of the second draw is white, but you don't know what happened in the first draw? Unless you can explain how this happened, you cannot ask the question of this probability. There is no probability to be computed. So finally, there is a deep and difficult study by Ian Hacking, a whole book called The Emergence of Probability. And the basic idea of the whole book is that the history of European philosophy and thought about probability created a space of ideas within which probability was formulated. This space of ideas was constrained by how people thought in Europe about various things which are discussed by Hacking. And so this is not a free choice. And what hacking says is that even today, the idea of probability we have, the concept is determined by those historical conditions, even though these historical conditions have now been forgotten. So basically what he is saying is that the probability concepts are operating within constraints created by history of European thought, and that is why they have not been able to step outside those boundaries. And this definition steps outside the boundaries created by the conditions of European thought. And that's why it is able to resolve problems which have not been resolved in uh, the theory of probability as it originated in Europe in the 17th century.